We are rolling. It's lecture 36, part 2 of L'Hopital's rule. We had the so-called standard indeterminate forms yesterday. We will finish those up with a kind of a messy final example, and then we'll move on to what are called other indeterminate forms. And it's our task to convert them to a more standard indeterminate form. So when I say standard indeterminate form, if we don't have one of the so-called standard ones, we'll take this limit of this rational function as x approaches a, and we know that if we get 0 over 0 or infinity over infinity, then we're in business to use derivative of the top, derivative of the bottom, try it again. So if we don't have one of those, for example, if we have, we'll encounter one today, I think this will probably be our last example, that looks like 1 to some infinitely large power. Well, you might think, well, 1 to the 6th, 1 to the 7th, 1 to the 100th, that's going to be 1, but we will look at 1 to the infinity power, and in fact it won't be 1. It's the value is close to 1, and the exponent's getting larger and larger. It could be a variety of answers. We'll have another example that is 0 times infinity. Something that's approaching 0, something else that's approaching infinity. I don't know, what do you want 0 times infinity to be? 17, okay? So here's a problem where 0 times infinity, let's say it's 17 over x, this is kind of a simplified version, times x as x gets infinitely large. Is this one approaching 0 as x gets infinitely large? Okay. Is this one approaching infinity? So it just so happens that before we allow x to approach infinity, whatever x is in the numerator, it also is in the denominator. So we could go ahead and strike those. Whatever number it is in the top, it's the same in the bottom. They reduce to 1. So this particular version of 0 times infinity is 17. So whatever you want the answer to be, you could make up a problem that would in fact have that. But if it's that simple, we won't make a big fuss about it and convert it to another form. But a lot of them will want to convert to this or this. Convert it to the standard indeterminate form. We have one more that is a standard indeterminate form. Pretty messy problem. It is actually in the book, but we're going to do it a little differently than it is done in the book. Which in a way kind of makes it a little messier. Tangent of x minus x all over x cubed. Is it an indeterminate form? We need to validate that before we apply L'Hopital's rule. Tangent of 0 is 0. X itself is 0, so the numerator is 0 minus 0. And the denominator is 0 cubed. So we do have 0 over 0. So it is legal, permissible, to apply L'Hopital's rule. And then try the limit again. Derivative of tangent x. Derivative of x. 1 all over x cubed. Derivative of x cubed, 3x squared. Well, you can certainly see an end to this because the denominator is 3x squared. So eventually we're going to get to the point where the next derivative is going to be 6x, and the final derivative that we would have to take would be 6. So you can kind of see an end to the problem. Unfortunately, the numerator is ugly at this point and gets uglier in the journey. Did we get to a point where we can have a solution? secant of 0. What's the cosine of 0? 1. So the secant ought to be its reciprocal, which is still 1. 1 minus 1 is 0, 3 0 squared, so we still have 0 over 0. Derivative of secant squared. 2 secant of x to the 1 times derivative of secant, which is correct, secant tangent. Told you it was going to get bad. Derivative of negative 1 is 0, so that's the numerator. Derivative of the denominator is 6x. So let me rewrite that as 2 secant squared x tangent x Now anything that's unaffected by x approaching 0 you can slide out in front, which at this point in time 2 is a factor of the numerator, 6 is a factor of the denominator, so we could bring those out front, 2 over 6 or 1 over 3. So that doesn't have anything to do with the fact that we have an indeterminate form. You can do that at any point in time in a limit problem. Do we still have 0 over 0? Secant squared of 0, that's 1 squared, that's 1. But tangent of 0 is 0, so the product is still 0 over x itself, which is 0. So we're still stuck with 0 over 0, but one more time through, we're going to have an answer. All right, so this is, sorry, I probably should put that. What are we doing to get there? We're using L'Hopital's rule for the third time. It is iterative. You can use it as many times as is needed in the problem. We have a product of variable quantities. So first, slide this down. Thanks. First times derivative of tangent, which is another secant squared, right? Plus second times derivative of first, 2 times secant x to the first times derivative of secant, which is secant tangent, all over the derivative of x, which is 1. So we are going to have an answer. I don't think you're going to have one really much worse than this one, which is why I think it's a good example to do in class. Secant to the 4th of x plus, what do we have here? 2 secant squared tangent squared. Is that right? We could factor out a secant squared. Let's just go ahead and see if we can get an answer. We know we're going to get something here. X is approaching 0. What's the secant of 0? 0. We already decided it's the reciprocal of the cosine of 0, which is 1. So that's 1 to the 4th, which is 1. Here we've got secant squared, which is 1 squared. This was actually 1 to the 4th. And tangent squared, which unfortunately is 0, so that drops that out, right? And we've got this 1/3 that we kind of factored out in front. So what do we have?
1/3.
1/3?
Yep.
So we do get a solution. Now, did you know or did I know that when we started this problem, the answer was going to be 1/3? And no earthly idea. So we start this problem, tangent x minus x all over x cubed. Do you know that's going to be 1/3? No. This is why this is called an indeterminate form. it takes on a lot of different answers depending on how it's given to us in the problem. So what is 0 over 0? In this problem, it's 1/3. Another problem, it might be 17, and another problem, negative 143. Questions on that problem before we leave it? A little bit different approach. If you look in the book, you'll see the same problem as an example. We approached it a little differently in the last step.
And so what is 1? What is the answer? Like, what
Well,
does it do?
we're stuck with this as part of the answer. And then after we did the third iteration of L'Hopital's rule and stuck in x equals 0 because x is approaching 0, we got 1 plus 0 all over 1. So we got 1 over 1. So it's 1 over 1 times 1/3, which is 1/3. So this particular version of 0 over 0 is 1/3. Another way, which is probably not nearly as accurate, is to graph the original problem. So if you were to graph this, what was it, over x cubed, and then examine that graph, not at 0 because it's not going to exist at 0, but near 0, you can probably see that it's close to this value. The only unfortunate thing is you don't know that it's 0.3 repeating or if it's 0.333128765. You don't really know that. I mean, your graphing calculator might tell you that it's 0.333 and maybe 4 or 5 of those 3's, but you don't know what follows. This way you can get an exact answer. And that might be helpful also to know that it's graphically pretty close to 1/3. All right, let's switch to other indeterminate forms. Use the board that's smarter than I am here. This first type of other indeterminate forms is this first type is 0 times infinity. And we had one brief example, one quick example. I said, what do you want 0 times infinity to be? 17. We got a pretty simple problem where the answer was 17. They're not all going to be that simple. So let's try this limit problem. X squared times natural log of x as x approaches 0. You have to put a little disclaimer up there. We have to approach 0 from the right. Why is that? Okay, we can't approach 0 from the left because one of these doesn't exist when you're using numbers slightly to the left of 0. And which function is that? Natural log. So natural log looks something like this. So it doesn't exist on the other side of 0, so we have to come in from the right only. So what do we have? We have x squared, which is 0 as x approaches 0. And we have natural log of x. And as x approaches 0 from the right, we're coming in here on this graph. What are the y values getting closer and closer to? Negative infinity, right? Way down there. So it is 0 times some version of infinity. This particular version is negative infinity. So let's convert it to a standard indeterminate form. So if I want to move the x squared, I don't want to change the problem, but I want to move the x squared from where it is in the numerator to where it is in the denominator. I want to leave natural log of x in the numerator. Right. If I put an x squared that's in the numerator into the denominator, it becomes x to the negative 2, which is 1 over x squared. Same problem. We're going to convert it to a situation where it's either 0 over 0 or infinity over infinity. What do we have now? By putting an x squared in the numerator to the denominator as 1 over x squared. What's the numerator?
ln.
Negative infinity. That didn't change. What's the denominator as x approaches 0?
0.
1 over some tremendously small number.
0.
It'd be a very large number, right?
Why?
Right? 1 over 10,000 is 10,000,
Oh.
right? So this approaches positive infinity. Negative infinity up here, we already saw that. And this approaches positive infinity. It doesn't really matter which version of infinity. It's infinitely large in magnitude. That's what matters. So we do have infinity over infinity. So we can use L'Hopital's rule. What's the derivative of the top? 1 over x. And if you don't like that 1 over x squared, think of it as Nicole said, that is x to the negative second. What's the derivative of x to the negative second? Negative 2, x to the negative third, which is negative 2 over x to the third. Is that all right? Now, anything that can be consolidated before we try to evaluate, let's do that. So we have a complex fraction. We have fractions within fractions. So we have 1 over x in the numerator, and we can multiply by the reciprocal of the denominator, which makes this a single fraction. So that's the problem we're dealing with. Does that help anything?
Yeah, you can take out an x.
Okay, x is, regardless of what x is, it's the same number, numerator and denominator, so we can knock that out. So this one knocks this down to x squared. So we have x squared, actually we have what? Negative 1/2, right? If I take that 1 and that negative 2, do we get an answer?
Not yet.
Yes.
We do,
Yeah.
right? Negative 1/2 is just a coefficient, so we'll just kind of leave that alone. What happens to x squared as x approaches 0 from the right? It's 0, right?
Yeah.
So negative 1/2 of 0, the final answer is 0. So we had infinity over infinity when we had what? 0 times infinity, which we converted to infinity over infinity. Apparently infinity over infinity in this particular version is 0. Another indeterminate form, other than the so-called standard indeterminate forms, is infinity minus infinity. Again, the goal would be to convert it to a so-called standard indeterminate form. Good trig example here. Cosecant minus cotangent. X is approaching 0. So let's just validate. We know it's going to be infinity minus infinity. Let's just validate that. Cosecant of 0, well, probably we're not wired necessarily to think of the cosecant of 0, but the sine of 0 ought to be up there somewhere. And then once we get the sign of 0, we'll try to flip it. What's the sign of 0? Sign of 0 is 0 over 1 or 0 over something. And then we flip it and we get something over 0, which is infinitely large, right? And cotangent, I don't know. Think of tangent. What's the tangent of 0 is same thing, right? 0. And we try to flip that, and it's infinitely large. So it is infinity minus infinity. Any suggestions, recommendations for somehow getting this difference to be, first of all, a single fraction, and hopefully a single fraction that is 0 over 0 or infinity over infinity? We're subtracting two things. We want to put them together.
Write them as common denominator.
Okay, write them as a fraction. And if we wrote each one as a fraction, how could we put two fractions together that are being subtracted?
Common denominator.
Common denominator. Okay? So cosecant, how could we rewrite that as a fraction? 1 over sine. And very conveniently, cotangent is cosine over sine, so they already have the same denominator. So if we didn't have the same denominator, we could get a common denominator, but we have one. So we really want the limit x approaches 0. So they have a common denominator, 1 minus cosine x all over sine x. And do we, at this point, have one of the standard indeterminate forms?
Yes.
Okay, which one?
0.
0 over 0. So if you put in 0, that would be 1. 1 minus 1 is 0. Sine of 0 is 0, so we've got the so-called standard indeterminate form. Tell me what to write. Tell me what to write next.
Take the
Derivative
derivative
of the top. What's the derivative of the top?
Negative sign.
Positive sine of x, right? This negative gets carried along, and the derivative of cosine is negative sine. So negative, the negative sign is sine.
Cosine.
And derivative of sine is cosine. That was way too easy. We have an answer now.
0 over 1.
0 over 1, which is
0.
0. Okay, so we do have an answer. If we were to continue, and we said, let's use L'Hopital's rule again because it's just fun, you know, and we just kind of get into it, and it's just really fun. Don't expect to get the right answer, because it's not going to necessarily work if it's not a indeterminate form. So sine of x over cosine of x as x approaches 0 is 0. So we had started with infinity minus infinity. Well, that kind of looks like it ought to be right, right? This particular version of infinity minus infinity, they were both about the same version of infinity. They subtract out, and it, in fact, is 0. Okay. This is a problem that you might recognize, but there's a whole category of other indeterminate forms. They could be of the form 0 to the 0, infinity to the 0. These are all kind of strange. And then we'll do an example right now that is 1 to the infinity. So these change from one problem to the other. They give different answers. Now, let's at least visit the 0 to the 0. We know that 2 to the 0 is what? Is 1. Why is that? Why is 2 to the 0?
Plus 2 not times itself.
Multiplying it to
Yeah.
I know, if you weren't multiplying it by anything, gosh, that ought to be 0. There's a good reason why 2 to the 0 is 1.
Because you're not multiplying itself by itself again. It's just 2, not multiplied again.
Okay, but that ought to be 2. 2 to the 0 ought to be 2.
Oh.
I mean, if we made our own rules, that to me seems like a more logical rule. But then 2 to the 1 would have to be something different, wouldn't it? If 2 to the 0 were 2, then 2 to the 1, we'd have to come up with a new, let's just make our own rules. How about how would you handle that?
1.
It's the same in the numerator and denominator, but don't we also have a rule that handles division of two things with like bases?
Yes.
What do you do?
The natural log is 2.
But what is 2 to the 3 minus 3? That's 2 to the 0. And what was the fraction that we started with that generated 2 to the 0? It was 1. There are other ways of validating that 2 to the 0 is 1, but that's one way. Do you see where that would fall apart with, instead of a 2 there, a 0 there? Everywhere I have a 2, if I would put a 0, that particular argument's going to fall apart, because I'd have a 0 in the numerator and a 0 in the denominator. There's the falling apart, that this isn't necessarily going to be true. So 0 to the 0 is one of these strange ones that varies from one problem to another. Let's look at an example with 1 to the infinity. Something that's very, very close to 1, but not exactly 1, and it's being raised to larger and larger powers. So this ought to be something that I think looks familiar. One plus 1 over x raised to the x as x gets infinitely large. Does that look familiar?
Mm-hmm. It's closer and closer to 1. Wait.
What is it? That's the number e.
E, yeah.
That's one of the definitions, actually, of the number e. So when we finish this problem, it is a 1 to the infinity problem. Doesn't this approach 1?
Yeah.
1 plus 1 over 600 trillion, that's pretty darn close to 1. And then x itself is approaching infinity, so we really do have 1 to the infinity. We expect, in this particular problem, 1 to the infinity, we expect it to be this strange number e. So let's validate that. How do we do that? We have to rewrite 1 plus 1 over x to the x.
Common denominator.
Just a little bit of background. What do we know about y equals e to the x and y equals natural log of x? They are what? Not reciprocals,
Inverses.
but inverses. These are inverses of each other. Because they're inverses, we know that e to the natural log of x is something, and the natural log of e to the x is something. So we're composing these two functions. What's e to the natural log of x? Let me rephrase that question so that it answers itself. What's e raised to the power that you would raise e to get x? It's x. What's the name of your brother whose name is Bob? That would be Bob, right? Not George. That'd be Bob. So you're raising e to a power. This power is the power you'd raise e to get x. This better be x. And that is true not because of saying it that way, but it's true because they're inverses of each other. You're composing two functions that are inverses. What's the natural log of e to the x? This is even more self-answering. You're looking for the power that you raise e to get e to the x. What power do you raise e to get e to the x? You raise e to the x to get e to the x. Again, you're composing a function with its inverse. So let's use this particular property of composing these two inverse operations. Let me generalize it a little bit. E to the natural log of u ought to be u. So let's relate it to this problem. E to the natural log, and this seems like overkill, way beyond what we should have to do to this problem. But it does get us to a place where we can solve it. What's e to the natural log of 1 plus 1 over x to the x? Good. It ought to be 1 plus 1 over x to the x. Whatever occupies that position, when you compose these, because they're inverses, ends up on the right side. So we have e to the natural log of this. It ought to equal this. So that's, in fact, what we're going to do to this problem. We're going to convert it to a base e problem. Forget about the base. It's not going to change in the problem. It stays e, and then we'll work only with the exponent. So this problem, our original problem, 1 plus 1 over x to the x, as x gets infinitely large, that looks awful. And I apologize for the fact that we've made a problem that was already kind of difficult looking. We've made it even worse. Actually, I've made it even worse. But it's actually going to get better. So this is e to the natural log of something. Is that something? So that's a legal substitution. Do you see anything at all that could be beneficial from this rewrite? What, Casey?
Bring down the x.
Okay, the x actually can come out in front now. So this fact that we had an x in exponent position, now this x, this guy right here, because we're dealing with the natural log of something to a power, that power can come out front in product form. I'm going to write way too many steps here, and you can consolidate steps, but this is the first type of problem we've seen like this, so I'm going to try to show each step. You can put steps together. Chandler?
Does the x go in front of the natural log or the e?
The natural log. Okay? So we have e to the x times same problem. Now let's put the limit in a sense where it belongs. The limit is not going to affect this number, but the limit involves x, so it does affect the exponent. So what we want at this point is e sorry, that's supposed to be an infinity. So e, not going to change no matter what happens to x in this problem. So we kind of abandon the e, but remember where we need to put our final answer. So we're going to continue with this problem. And just remember when we're done that that's not the answer, it's e to that power that's the answer. Be nice if I knew how to spell. So this was just the exponent. That's the only thing we're going to look at the rest of the way. X times natural log. And remember, we haven't understood E right here. So when we get an answer, it's the power to which E is being raised. What do we have?
Infinity times one.
This is infinitely large, right? What about the natural log of 1 plus 1 over x? I'm glad I saved this much time for this problem. I was thinking we were going to be done way too early, but this problem, this is a battle.
It's kind of approach 1, so the natural log.
Okay,
of 1.
this whole thing, that's correct, is approaching 1, and what's the natural log of 1?
0.
0. So this is approaching 0. So what we have is that type of other indeterminate form. We started with, what, 1 to the infinity, and we've kind of converted it, hopefully, to a place where we can analyze it. At this point in time, it's a little better, but it's not great. We need to rewrite this as one of the so-called standard indeterminate forms. How about if we left the natural log? We did this on a problem before, and it got us somewhere. Let's try this again. Leave the natural log in the numerator. The x that's in the numerator, throw it to the denominator, calling it what?
X to the negative 1.
X to the negative 1, or 1 over x. Now, I have a good idea that that's going to work because I've got a 1 over x in the numerator and I've got another one in the denominator. I'm thinking that those eventually, when we take the derivative, those two things have the potential of knocking each other out. All right, what's the numerator now?
0.
0. What's the denominator? What's 1 over some infinitely large number?
0.
That's 0. So we have 0 over 0, right?
Yes.
So we can use L'Hopital's rule. Finally. That's what I say. The numerator is covered up. It was the natural log of something. What's the derivative of the natural log of something?
1 over all of this.
1 over that something. Wasn't it 1 plus 1 over x?
Yes.
Right? Times the derivative of that something. What's the derivative of 1 plus 1 over x? Derivative of 1 is 0. What's derivative of 1 over x?
Negative.
Negative x.
Negative 1 over x squared.
Yes.
So that's the derivative of the top. At the natural log of something, the derivative is 1 over that something times the derivative of that something, which is negative 1 over x squared. Denominator now is easy. What's the derivative of 1 over x?
Negative 1 over x.
Negative 1 over x squared. All right, so tell me what to do. Besides, be quiet and finish up so we can get out of here. I know that. You don't have to tell me
Taking
that.
infinity, it's 1 times negative.
Okay, these knock out.
Yeah.
This one and this one reduce. So we should be left with just that other term in the numerator. One over 1 plus 1 over x. And let's go ahead and plug in and see if we are kind of done with the indeterminate forms. I think we are,
Yeah.
right?
Yeah.
So the answer is numerator is 1, denominator is 1. So 1 over 1, which is 1. So the answer to this problem is 1. Incorrect.
E to the 1.
Remember, this was the power to which we were raising E. So we go back and pick up that. So we had at one point in time E to the limit of x natural log of 1 plus 1 over x as x was approaching infinity. We just found out that this portion was in fact equal to 1. So it is e to the 1, which is just e. What did we say this was when we started the problem? We said it was the definition, one of the definitions of the number e, and we in fact validated that with converting it to different forms of indeterminate forms. Let me preface what we're going to do tomorrow, because I have the time to do it, and I very rarely have the time to do it at the end of class. We are going to embark on what some people feel like are the more difficult problems in all of Calc 1. They are max-min word problems. And we'll do as many problems as we can, because I think the more you see of max-min word problems, sometimes they're called optimization problems. We're going to use first and second derivative on equations that are not written for us, but equations that we come up with on our own. So we're going to read a word problem. We're going to try to determine what it is that's trying to be maximized or minimized. Minimize the surface area. Why would you want to minimize the surface area? Because it's made out of platinum, and platinum is expensive. So it might be helpful to minimize the surface area, but yet enclose a fixed volume. Okay? Why do you think you've got some unique soda can back there? That's not the kind of the standard can. It's a little taller, right? Yeah. It's a good thing it's not in a brown paper bag. But how did that come about? That some, I mean, don't you think they had to pay for, what do you think that is, aluminum?
Yeah.
Right? That's an aluminum can. So think of a beverage can, not adult beverages because you're not of age. But you've got this beverage can that could take on a lot of different shapes and hold 12 fluid ounces, right? It could be this real tall, skinny can, and you could, like bring it back and try to drink out of it this way. The drink machines would probably have trouble with that. So you say, well, maybe it ought to look like this. It could hold 12 ounces and look like that, right? So we'd, hold on to it with both hands and we'd drink out of it. Well, there are some good reasons why the can has that shape. One is because most people's hands fit around it. They don't fit around this, and they fit around this one twice. So both of these would be kind of annoying to drink out of. So that's part of it. But also part of it is somewhere in here in this problem is the can, the way we like to drink a beverage out of it, which is something like this. It probably, to a certain extent, minimizes the surface area because those bottlers and canners, they have to pay for that aluminum, right? So this probably has more surface area, and this probably has more surface area. This probably is pretty darn close to the minimum surface area. So that's the kind of thing we're going to do. We're going to take a word problem. We're going to put it into an equation. Guess what we'll do with the equation? We'll take the first derivative of it. Why? Because we want to know, is it one of these kind of points, if we were to graph it, which is a relative max, what types of things would we want to maximize? How about profit? What else? Money. Profit. Okay, revenue. What kind of things might we want to minimize? We might want to minimize surface area because we got to pay for it. We might want to minimize cost. There's a lot of things, like inventory, what it takes to maintain a certain product on hand and what it takes to store them and to reorder them. You might want to minimize the inventory cost. So we'll come up with problems. They do have graphs. Very rarely will we graph them. But we'll come up with a surface area equation, and we will do calculus with that. We'll take the derivative, and we'll set it equal to 0. We'll take the second derivative, and we'll see if it's concave up or down to see if we're really dealing with a max or a min. but they're word problems. So buckle up. Tomorrow is kind of an adventure. See you tomorrow.